All right, so if you've watched the last two videos and you're still with me, we're now going to combine the number of bedrooms and the number of bathrooms with a multiple linear regression model to try to understand how bedrooms and bathrooms together influence the price of an apartment. So what we have is monthly rent on 40 apartments, and then for each of those apartments, we know the number of bedrooms and the number of bathrooms that they have. What we've seen earlier is that individually, both number of bedrooms and number of bathrooms are statistically significantly related to the price of an apartment. As the number of bathrooms goes up, so does monthly rent. As the number of bedrooms goes up, so does monthly rent. When we look at these individually using linear regression, we can see that when it comes to number of bedrooms, it explains 74% of the variation in monthly rent if it's the only thing in the model. And it's statistically significant at the 5% or even 1% level, and we can conclude that if beds are the only independent variable, we'd expect each bedroom to result in an additional $401 per month in rent. When it comes to bathrooms, the R-squared, the coefficient of variation, is a little bit lower. If we only have data on bathrooms, we can only explain about 52% of the variation in rent, 52.91. The coefficient is still statistically significant at the 1% or 5% level, and each additional bathroom we can conclude would add on average about $378 to the price of an apartment. But what if we make a model that looks like this? Our estimated rent, y hat, is equal to an intercept plus beta 1 times the number of beds plus beta 2 times the number of bathrooms, right? This is a multiple regression model now because we've got two independent variables, which means that we essentially have two null and alternative hypotheses to test. We'll test beta 1 for statistical significance, and we'll test beta 2 for statistical significance. And in both cases, the hypothesis is the same. The null hypothesis is always that beta 1 is equal to 0 and beta 2 is equal to 0. And the alternative is that it's not equal to 0. Excuse my typo. I could start the video over, but I'm not going to. So we've got two null hypotheses. Two hypothesis tests, one for beta 1, it is or isn't equal to 0, and one for beta 2, it is or isn't equal to 0. And in both of these cases, each line will come with a coefficient and a p-value, and the p-value is the probability that the corresponding null hypothesis is true. So we get a p-value, we get one for each variable, or one for each variable, one for each coefficient, but the model only has one coefficient of determination. And in this case, because we have a multiple linear regression model, we're going to look at the adjusted R-squared. That's the coefficient of determination that you use when you've got more than one independent variable. And after we walk through this, we're going to just compare the coefficient of determinations from this model and the other two to figure out which model does the best job at modeling or predicting monthly rent on an apartment. So let me zoom out. I need to get the data. Great, same data. Rent, bedrooms, bathrooms. Data analysis, regression, okay. We still have our Y input range is the same because we were just in the video before, but A1 to A41, all those. The X input range now is going to be a little bit different. I'm going to highlight all of the X variables. They do have to be right next to each other. I've got labels, and I want to put them somewhere new. How about here? And I'll say OK. Then let's just format. Why not? And then let's make sure everything's wide enough, and then let's remove these second confidence intervals because why not? Okay, now let's take a look at our model. Our adjusted R squared, 0.7694. This is the coefficient of determination for a multiple linear regression model. Significance F here tests the null hypothesis that all of the betas, beta 1 and beta 2, are equal to 0. So the p-value here is the probability that we can't use this model at all, that beta 1 and beta 2 are equal to 0, and that's 0, right? It's not probable. If that, as long as that's less than 0.05 or 0.1, our model's good, but this is a good model. It's 0. So now let's come down here and take a look at the coefficients for our two x variables. So we've got bedrooms and we've got bathrooms. This makes that coefficient beta 1 and this coefficient beta 2. So let's start with our first null hypothesis. The first null hypothesis being that the number of bedrooms is unrelated to rent for an apartment. So if the number of bedrooms was unrelated, it would mean that this coefficient was actually 0, right? But this is the probability that that's 0. It's not 0. The number of bedrooms influences the rental price on an apartment. And that's statistically significant at the 5% level and at the 1% level. Basically, this says that now that we've got bedrooms and bathrooms in our model, which explains 76% of the variation in house and rental prices, an additional bedroom adds $315.96 per month. But then now if we look down here at baths, that 141.46, that's beta 2. Is it equal to 0? Well, no, it's equal to $141.46, but more specifically, can we conclude statistically significantly, like, is this really different from 0? What's the probability that it's actually 0? Well, 0.01, right, is significant at the 5% level and at the, not at the 1% level, because that is not less than 1%, right? It is 1%, it's 1.3%. But it is statistically significant at the 5% level, and that's what we are being asked to look at. I said 1% here, but I meant 5%. We're looking at the 5% level. So both of these are statistically significant at the 5% level. At the 1% level, bathrooms wouldn't be. We'd say, we can't be totally sure that it's not really more bathrooms doesn't make more rent. But at the 5% level, we're willing to say the probability that that's 0 is only 1%. If we think back to what we know about hypothesis testing is that the standard error on the number of bathrooms is 54. And so this coefficient is 2.62 standard errors away from the mean. That's what that t-stat is. So if that means something to you, you might say, oh yeah, that's pretty far away. Okay, so now looking at this multiple linear regression model, we can conclude, we can reject the null hypothesis that the coefficient for bedrooms, beta 1, is 0. And we can, in support of the alternative hypothesis, which is that it's not 0. More bedrooms means more rent. If we look at bathrooms, we can reject the null hypothesis that the number of bathrooms isn't related to rent at the 5% level, and we can say more bathrooms, more rent. So if I write this up, insert text box, I'm going to add another little piece to this conversation, which is we've made 3 models now. We've looked at bathrooms and bedrooms independently, and we looked at a multiple regression model that contains both bedrooms and bathrooms. What would we learn? Well, if I compare the coefficients of determination, which for a multiple regression model is adjusted R squared, with the coefficient of determination for my two simple linear regression models, I can see that the R-squared for my multiple linear regression model is the highest. It has the best explanatory power. It's going to do the best job at helping us predict what monthly rent is going to be if I know bedrooms and bathrooms, and I use both of them. I'm going to explain more of the variation in prices. I'll have smaller errors, right? I'll get better. So in this case, this multiple linear regression model is the best. And how I might phrase it is, in comparison to the simple linear regression, the multiple linear regression model has higher explanatory power or higher predictive power with an adjusted R-squared of 0.7694. This model explains 76.94% of the variation in monthly rents. If we want to use this data to predict rental values, we should use the model that contains both bedrooms and bathrooms as independent variables. The coefficient on bedrooms is statistically significant at the 1% level and indicates that each additional will increase rents on average by $315.96. The coefficient, right? So the coefficient is right there, and that's the slope. We have multiple regression, so we've got more than one slope, and so it's a little bit funnier to interpret because you can't see it all in a plot like you could when it was only one variable. The coefficient on bathrooms is statistically significant at the 5% level. Why? Because this is greater than 1%, so we wouldn't say it's significant at the 1% level, but the next cutoff is 5%, 1, 5, and 10. And suggests that each additional bathroom will raise the price of an apartment. Oh, no, you don't. By $141.46 per month. Whew. How do you feel? Not too bad, right? Okay, and the significance of F, again, just tells us that it is the test of joint significance, that beta 1 and beta 2 both equal 0, which the probability of that is 0. Because if either beta 1 or beta 2 is statistically significant, right, it doesn't equal 0, then this will always be significant. And if you only have one model or one variable, like these, beds and baths, you know, they're going to match more or less. Okay. I hope that was real good fun for you. It was real good fun for me, and I will see you in class or on the internet or wherever. Happy calculating. Bye.